Dear student, so yesterday I have taken the functions of the mitochondria, and categorically I have mentioned that this function of the mitochondria is divided into four stages, mainly four stages known as glycolysis, pyruvic acid oxidations, then Krebs cycle, and then electron transport systems. In my earlier classes, I finished what during the glycolysis and deformation of the glycolysis, then how pyruvic acid undergoes the oxidations, and after that this pyruvic oxidation is converted into acetyl coenzyme A, and that acetyl coenzyme A it enters into a cycle which is popularly known as the citric acid cycle or the Krebs cycles. So that much I have discussed in my last class. Today I am going to discuss regarding the electron transport chains. Now this electron transport chain, it is located in the inner membrane of the mitochondria. It consists of, it is embedded in the inner membrane of the mitochondria. It is mainly consists of 5 complexes. Out of that 5 complexes, 4 complexes, the complex 1, complex 2, complex 3 and complex 4, and 2 coenzyme, one is coenzyme Q electron carrier and the cytochrome C electron carrier. So these form the what electron transport chains. And fifth number, that is the F0 and F1 particles, which has concerned oxidative phosphorylations. So this is the very basic structure of the electron transport chains. So in my next slide, just I would like to show the electron transport chain. So electron transport chain, it is embedded in the inner membrane of the mitochondria. So you see there is a 2 sides. One is the mitochondrial matrix site and another is the intermembrane site. Now these electron transport systems, they will transfer electron and hydrogen proton from the matrix site to the cytoplasmic sites. So in this picture it is given the complex 1, then complex 2, complex 3, then complex 4. Okay, now this complex 1, 3 and 4, it concerned with transfer of the electron or the proton from M site to the C sites. Okay, and simultaneously this electron will be what? It will be carried by the coenzyme Q, and then it will be taken by the cytochrome C, and lastly it will go to the there is complex 4, and in the complex 4 this electron combines with the half of the there is oxygens and hydrogen proton, and ultimately it will give rise to the water. Now during this electron and hydrogen transport, hydrogen will be what transported at 3 sites. One is complex 1, one is the complex 3, and then is the complex 4 from there is M site to the C sites. So in my next diagram, I am showing the location of different complexes of the inner membrane and F0 and F1 particle. Now see, this is the very good structure of the mitochondria. So these two are the outer membrane, and this is the what inner membrane. Now these mitochondrial complexes, that is complex 1, 2, 3, 4, 5, all are embedded in the inner membrane of the mitochondria. So this complex 1, this complex 2, complex 3, complex 4, they are embedded in the inner membrane of the mitochondria. There are so many complexes will be there in the inner membrane of the mitochondria. For our convenience, we are showing the 1, 2, 3, 4, or this one also you can say 1, this 3, 2 is not shown here, 1, 3 and 4. Okay. And fifth complex, that is the another complex which is also that is associated with this inner membrane of mitochondria. Thing is that from the matrix, okay, all the hydrogen proton electron which are generated, they will be transferred from the M site to the C site. Okay, that is outer membranes or the intermembrane space. As a result, this ionic gradient will be produced. This hydrogen proton will be more here, and OH will be more. As a result, outside will be positively charged and inside will be negatively charged. Now this hydrogen proton, to minimize this redox potential or membrane potential, hydrogen proton tries to enter inside, but they cannot enter. Okay, there is only one way they can enter through this. There is a complex, there is a 5, or which is known the F0 and F1 particles. So I will give the details in my next slides. So electron transport chains. The electron transport chain is a collection of the membrane embedded proteins and organic molecules. Most of them are organized into 4 large complexes, level complex 1 to complex 4. There is 1, 2, 3, 4 and 4. In eukaryotes, many copies of these molecules are found in the inner mitochondrial membranes. As the electron travel through the chain, now you see 2 hydrogens are generated already, you know, during the glycolysis, during the pyruvic oxidation, during the Krebs cycle. Now hydrogen protons, they will be broken down into hydrogens, nascent hydrogens will be broken down into hydrogen proton and electrons. Okay. Now hydrogen, proton and electrons, they are carried by the same system which is popularly known as the electron transport chain. Though it is known as the electron transport chain, alternative name is the hydrogen transport chains. As the electron travel through the chain, they go from higher to a lower energy level, moving from less electron hungry to a more electron hungry molecules. Energy is released in the downhill electron transfer, and the several of the protein complexes use the released energy to pump the protons. From the mitochondrial matrix to the intermembrane space forming a proton gradient, the complex of the ETS are as follows. So in my next slide, I am giving there is a different complexes. So first complex 1, which is popularly known as NADH. NADH is very good at donating the electrons in redox reactions. That is, its electrons are at a high energy levels, so it can be transferred the electron directly to the complex 1. Okay, turning back to the NAD++. Now we see start the superscript plus and the superscript. Now we see NAD is a nicotinamide adenine dinucleotides, NAD plus. Now when this NAD plus plus or NAD plus, it accepts the hydrogen, NAD will be what? It will from the oxidized to it will reduce, it will enter into reduction test NADH. Okay. So when it is reduced to NADH, okay, it will go to the outer membrane space, and in the outer membrane space what will happen? Hydrogen will be released from the NADH. As a result, NAD again it will come to the original state, which is known as NAD plus. Now in this way, once it will remain in the oxidized states, another it will remain in the reduction states. In this way, hydrogen will be shuttled from the M side to the C sides. So first complex I have shown, this complex 1. Next complex is known as FADH2, is not a good at donating the electron as NADH. Okay, so it is cannot transfer the electron to the complex 1. Instead, it fits them into the transport chain through the complex 2, which does not form the proton across the membrane. Now, this FADH2, that means it accepts the hydrogen when it is released from the succinate. Now, FADH, it will be that means when it will release the hydrogen, it will be converted into FAD. Okay, again it will be oxidized, that is FAD, and there is reaction to FADH2. In this way, hydrogen will be transported. But one thing it must be noted that the FADH2 never releases the hydrogens. So the complexes of the FA, that is details of the complex 1 and complex 2, I have given in my next slides. Now you see complex 1. The scientific name of the complex 1 is known as NADH coenzyme Q oxidoreductase. Entry side is NADH plus hydrogen proton. It contains iron sulfur clusters, that is non-heme proteins, and flavin mononucleotide phosphates. So after this complex 1, there will be complex Q, that is free in the membrane, that is electron carrier. So net reaction NAD plus hydrogen plus coenzyme Q. So you will get NAD. So this is the reduction phase NADH. It will be oxidized to NAD plus, and this coenzyme Q will be again reduced to coenzyme QS2. And delta G0 is minus 81.0 kilojoules per molecules. Complex 1 pumps the proton outside the mitochondria, which help in the ATP productions. Now in my next slide, this is the complex details. I have given the details of the complex 2. Now complex 2 is a succinate coenzyme Q reductase. Earlier one is also coenzyme Q reductase. Here also this is also coenzyme Q reductase. Okay. So coenzyme Q, there is a coenzyme Q is connected to the complex 1 as well as the complex 2. That is coenzyme Q lies in between the complex 1 and 3 and this complex 2 and 3. So that is why it is a common coenzyme Q, a common carrier, electron carrier. So entry side is the FADH2. It contains FES sulfur, clustered non-heme protein, and coenzyme Q that is free in the membranes. Net reaction succinate plus coenzyme Q, that is it will convert in the fumarate plus coenzyme QS2. So this is oxidized state, this is the reduced states. And delta G0, this is the free energy, is minus 13.5 kilojoules per molecule. Conversion of succinate to fumarate is reaction is a TCA cycle and is catalyzed with the succinate dehydrogenase. Not a proton pump, no ATP produced. So in my next slide, just I will discuss regarding the complex 3. Now complex 3, the position of the 1 and 2 when over, then coenzyme Q. After the coenzyme Q, the next complex will come is on the complex 3. Complex 3, it includes the non-iron sulfur protein, but it also contains two proteins of another type known as the cytochromes. Cytochromes are a family of related protein that have heme prosthetic group containing the ions. In complex 3, electrons are passed from one cytochrome to to iron sulfur protein to a second cytochrome, then finally transferred out to the complex to a mobile electron carrier, which is popularly known as coenzyme Q. Coenzyme Q lies between the complex 1 and 3 and 2 and 3. Okay, complex 1, and there is a complex 3 pumps two hydrogen from the matrix into the intermediate space. So complex 3, now in my next slide I will give the details of the complex 3. Now complex 3, you see coenzyme QS2, coenzyme QS2 cytochrome C oxidative reactase. It contains the cytochrome C, cytochrome B, and cytochrome C1. So these cytochrome B, C, B, C1, these are the they are part of the enzymes. Okay, the oxidative, that is a complex 3, that is part of the complex 3. So these are the subunit, better to say the subunit C, B, and C1, and several iron sulfur clusters, the non-iron protein, it remains associated with this complex 3. Okay, net reaction is coenzyme QS2 plus 2 cytochrome C, okay, along with the iron sulfurs. It will give rise to coenzyme Q, 2 cytochrome C. So iron is from ferric to the ferrous states, and 2 hydrogens, okay, liberated. And delta G0 is minus 34.2 kilojoules. Complex 3 pumps protons outside the mitochondria. Now complex 3 is the it is the region where mitochondria will be the hydrogen will be transported from the M site to the C sites. So during this that means translocations, that hydrogen proton, it will help in the production of the ATP. Okay. So in my next slide I will give I would like to discuss again the complex force. Complex force from complex 3 electron carrier, that is the cytochrome C. The electron carrier, that is the cytochrome C, delivers electron to that is the last electron transport chain, that is known, it is chain complexes, which is known the complex force. There the electrons are passed through the two more cytochromes with the help of a nearby copper ion. It transfers electron to half of oxygen, splitting oxygen to form the two molecules of the water. The protons, that is 2 hydrogen used to form the water, come from the matrix. Okay, and the complex 4 also pumps the proton from the matrix to the intermembrane space. Here one thing you must be notice, okay, that hydrogens are when carried by the NAD, FAD, okay, or the complex 4, they will transfer from M site to the C sites. Okay, simultaneously electrons are also carrying on, but electrons are coming on to the complex 4. After coming to the complex 4, hydrogen from the matrix and half of oxygen from the matrix, they combine together, ultimately they will give rise to the waters. Okay, so these are the details. In my next slide I am giving the details of the complex 4, which contains the cytochrome A, A3, and then net reaction is 2 cytochrome, that is plus Fe2, half of oxygen plus hydrogen, cytochrome Fe3, and waters. So already I have explained earlier also. Delta G0 minus 100 kilojoules, complex 4 proton outside the mitochondria, and ATP is produced. So in my next slide I will show you how that means there is protons when transferred from matrix side to C side. As a result, they will produce high free energy. Okay, and this high free energy, it also creates that is our electron potentials. So from the high electron potential, so NAD, first NAD is the acceptors. Okay, then from the NAD it is a part of the complex 1 NAD, then it will go to the FAD, the electron will move to the FAD, and hydrogen will be transported to the C side. The electron will go to the FAD, from FAD it will go to the coenzyme Q. So now say coenzyme Q, it lies between the complex 1 and complex 2. Okay, not lie between the complex 1 and complex. Electron will come from the complex 1 to complex 2 and complex 2 the coenzyme Q. The coenzyme Q, it lies in between the complex 3 and 1 and 3 and 2. Okay. Next what will happens, this electron from the complex 3, it will move to the cytochrome C, okay, which is the part of their complex 4, and ultimately that electron ultimately come into the again matrix sites. Okay, that electron again combined in the half of there is a hydrogen and oxygens, and ultimately it will give rise to the waters. So in this slide I have shown how the transport chain is going on, and free energy is moving from higher potential to the lower potentials. So in my next slides, in the components of the electron transport systems. So already I have explained earlier, the electron transport chain, the electron carriers are arranged such that the flow of the electron is spontaneous. Each acceptor has a sequentially greater electron affinity, the greater electron potential, this delta E 0. Then the electron donors. The series of oxidational reaction requires 4 membrane bounds multi-protein complexes called the complex 1, 2, 3 and 4. Each complex consists of the multiple proteins and iron sulfur heme or a copper phosphoric groups. Okay. Complex 1, 3, 4 are the proton pumps. And complex 2 consists of the succinate dehydrogenase, the enzyme TCA cycles. And complex 4 ultimately transfer of the hydrogen, it will help in the generation of water molecules. So in my next slide, I would like to discuss what is a chemiosmotic theory. Now it has been mentioned in your syllabus, that is what do you mean the chemiosmotic theory. Now before studying the chemiosmotic theory, let me say that cellular oxidation, it consists of mainly 4 phases, which is the glycolysis, which takes place outside the mitochondria, that is the cytoplasms, and the end product, that is the pyruvic acid, enter into the mitochondria matrix, and it will undergo there is first oxidation, pyruvic acid oxidations. As a result, there is a formation of the acetyl coenzyme A. This acetyl coenzyme A, next it enters into another cycle, which is popular in the citric acid cycles. Okay. As a result, there is the liberation of the hydrogen protons. Okay, hydrogens. So these hydrogen will be broken down into hydrogen proton and electrons. Now hydrogen proton and electrons are what? It will be carried by our electron transport chains. Okay. Now we see when these hydrogen are transported from M site to the C site, then there is a ionic differences are creates. Outside become the positive charge and inside become the negative charge. Okay. As a result, there is a phenomena which is popular in the chemiosmotic theory. The chemiosmotic theory explains the mechanism of the oxidative phosphorylations. When electrons are transported along the components of the electron transport chain, the accompanying protons are released in the intermembrane space in between the 2 membranes. The resulting uneven distribution of the proton generates a pH gradient. There is ionic gradient and pH gradients. Okay, hydrogen ion gradients creates, and a charge gradient across the inner mitochondrial membranes. The electrical potentials energy generated by this gradient is called the proton motive force. The return of the protons to the mitochondrial matrix is coupled in the ATP synthesis. So in my next diagrams, just I have shown, you see this is in the glycolysis which takes place in the cytoplasms. Okay, this is the starting molecule glucose, and the end material is on the pyruvic acids. Now pyruvic acid is a 3 carbon compounds and glucose is a 6 carbon compounds. The pyruvic acid now enters through the mitochondrial membrane. This is the outer membrane and this is the inner membranes. When it enters into the inner membrane, this pyruvic acid undergo oxidation, which is popularly known as acetyl coenzyme A. Now this acetyl coenzyme A, during the liberation of acetyl coenzyme A, there is a liberation of the hydrogen protons as well as the carbon dioxide. Now acetyl coenzyme, it enters in the 3rd cycle, which is popularly known as the citric acid cycles. As a result, there is the liberation of the so many hydrogen protons. Okay. So these hydrogen protons are what? Either it is accepted by NAD or it is accepted by the FAD. Now this NAD, FAD, they are located in the inner membrane of the mitochondria. So this is very nicely, it has been shown here. So this is the, let's say, NAD, FAD, they are arranged complex 1, complex 2, complex 3 and complex 4. Okay. So as a result, what will happen? Hydrogen protons are what? It will be transferred from the M side to the C side. So here is the hydrogen, hydrogen, hydrogen. Now C side will be what? It will be pH will be there will be acidic, and here it will be alkaline, and here the high pH is plus and there is a OH minus. As a result, there will be what? There will be a proton motive force is created, which is popularly known as the chemiosmotic phenomena. Now, this hydrogen cannot enter to the inner membrane because inner membrane is very impermeable. There is only one way through which the hydrogen proton it can enter, that is known the F0 and F1 particles, or it is also known as known as there is a complex 5. Popularly, it is known as complex 5. So, in the next diagram, I am showing how this complex 5 it helps in the oxidative phosphorylation. Okay, what I have discussed, that is known as the electron transport chain. That is, electron as well as the protons are what transported by electron transport chain, and complex 1, 2, 3, 4 are responsible for what? For transfer of the electron as well as the protons. Now, complex 5, which is F0 and F0 and F1 particle, which is mainly what? It helps in the conservation of energy, or which is popularly known as oxidative phosphorylations. Now, let me say what is the oxidative phosphorylation. The oxidative phosphorylation, or the Atp synthase, the electrochemical potential energy generated by the proton and the pH gradient across the mitochondrial inner membrane is called the proton motive force and is used to drive the Atp synthesis. First point. The proton return to the mitochondrial matrix through a integral membrane protein known as the complex 5 of the ETS, electron transport systems. ETC means electron transport chain and ETS means electron transport system. Electron transport system consists of all the 4 ETC plus complex 5. Now, ATP synthesis is a multiple subunit complex that binds the ADP and inorganic phosphate and converts them into the ATP. Proton transport is coupled to ATP synthesis. This is called the chemiosmotic theory of the oxidative phosphorylation I explained earlier. ATP is not synthesized unless there is a simultaneous transport of the hydrogen proton across the inner mitochondrial membrane. In my next slides, I will show you the diagrams of the that is known as the inner membrane. Now, in this diagram, very nicely it has been shown. Now you see, there is complex 1, complex 2, complex 3, and complex 4, all the complexes. Okay. Now, complex 1, 3, and 4, it helps in the transport of the hydrogen proton. And these electron carrier, one is coenzyme Q and cytochrome C, it helps in the carrying of the electron. And finally, the electron coming when it enters to the 4, then the electron plus hydrogen, okay, this hydrogen plus this 2 hydrogen plus 2 electron plus half of oxygen, okay, they combine together, ultimately they form the water, and this water, 2 molecules of the water, it is multiplied by 2, ultimately 2 molecules of water. So, this happens in the mitochondrial matrix, okay. Simultaneously, I already have mentioned that as a result of the transport of the hydrogen proton from the M side to the C side, there is the creation of the ionic gradient. So, this ionic gradient, it can be minimized by how? When these hydrogen protons are channeled through these F0 and F1 particles. Now, there is a channel, there is a proton channel is there. Through this proton channel, hydrogen proton will be, they will be what? They will enter this proton channel. When hydrogen proton will be what? It will be transported to this proton channel. Then already in the headpiece of this F1 particle, there is a ADP is there, inorganic phosphate also there, and one enzyme is known as ATP synthase. Okay, so ATP synthase is the enzyme, or ATP synthetase is the enzyme which is present in the headpiece of the F1 particle. Now, this when this hydrogen proton are it enters to the proton channel, then ATP synthase will be activated. When ATP synthase will be activated, then they will help in the coupling of the ADP and inorganic phosphate, as a result of which there is a creation of the ATP, which is the high energy currency of the cells or the living organisms. Okay. In my next slides, I am showing the flow of the electrons during the oxidative phosphorylations. So, already earlier also I have shown you the 2 hydrogen, it will be excited by NADase. Okay. When this NAD will accept it, it will convert into NADase. Okay. Now, ultimately, this hydrogen proton will be transported from the M side to the C side, and electron will channelized in the coenzyme Q. Simultaneously, complex 2 also accept 2 hydrogens when the hydrogen is released from the succinate. Okay. Then again the hydrogen will be what this hydrogen or the electron will be channelized in the coenzyme Q. Okay. Next is what the complex 3. In the complex 3 again hydrogen will be channelized from M side to the C side, and that electron which is coming from the coenzyme Q and ultimately will be channelized to the cytochrome C. Okay, and from cytochrome C the electron ultimately it will enter into the complex 4. Similarly to hydrogen also accepted by the complex 4, that is cytochrome C oxidase. Okay, so hydrogen will be transported from the M side to the C side, and finally the electrons, that is electron combined with the hydrogen and oxygen, ultimately it will give us the water which formation takes place in the inside of the matrix. Outside there is a 3 places, the complex 1, complex 3 and complex 4 are concerned with the transport of the hydrogen proton from the M side to the C side. Very nicely I have shown the diagram here. So flow of electron during the oxidative phosphorylation. Now you see in these diagrams just I have shown the electrons and hydrogen protons are what accepted by either NAD or it is FAD. So this if it is NAD then complex 1, then if it is FAD complex 2. Ultimately it will shuttle into the coenzyme Q. Okay, from coenzyme Q it will go to the coenzyme 3, and from the coenzyme 3 what will happen, it will be it will go to the cytochrome C, and from the cytochrome C it will go to the complex 5, complex 4. So ultimately the electron it helps in the generation of the water molecule. Simultaneously from all these complexes except the complex 2, what will happen, there is the liberation of the hydrogen, there is a transport of the hydrogen from the M side to the C side. Now this hydrogen proton, they will be forced, there is some proteins are there which is popular in OSCP, oligomycin sensitizing conferring protein. So this oligomycin sensitizing protein have a coupling force, okay, through which what will happen, they will bring all the hydrogen proton to enter in the complex 5, F0 and F1 ATP synthesis. Okay, as a result what will happen, ADP and inorganic phosphate they will couple, and ultimately there is a creation of the ATP or adenosine triphosphate 189 is combined to the 3 phosphates, adenosine triphosphates. So this is the what overall view of the there is our ATP synthesis. Now in this diagram again I am showing, so this is the inner mitochondrial membranes. Okay, inner mitochondrial membrane. Now first there is the acyl coenzyme comes from the cytoplasms. This acyl coenzyme A, it converts in the Krebs cycles. Okay, so as a result there is the creation of the hydrogen protons. So these hydrogen protons are low orbitally accepted by NAD, FAD. Okay, so ultimately it will be transported from the your M side to the C side, the hydrogen proton, hydrogen proton, hydrogen proton. Now all these hydrogen proton again they will coupled, they are forced to enter through the what? Forced through these F0 and F1 particles. When this they will coupled through this F0 and F1 particle, then ADP and then inorganic phosphate, which is present in the headpiece of the there is F0 and F1 particle, they will couple and they will give rise to the ATP. Okay, and then this ATP will perform the different function and they will be channelized from the mitochondria to different parts of the our reaction. There is another part that is not our syllabus. I am not going to discuss that one. So I am showing in my next slides what is the structure of the F1 particles, F1 and F0. Now there is F0 and F1 particle. You see, F0 is a part of the particle which is embedded in the inner membrane of the mitochondria. So this is the inner membrane of the mitochondria, and this F1 always it remain project in the that is a matrix of the mitochondria. Now you see, so this is 2 alpha, 3 alpha and 3 beta subunit. Total 6 units are there in the head piece. This is the stalk and this is the base piece. And this is the structure of the protein. This is the structure of the protein. Okay. So in this picture, the fine structure of the what there is F0 and F1 particle, it has been shown. Okay. In my next slides, the structure of the F0 and F1 particles. Now, ATP synthesis is a ubiquitous membrane enzyme that plays a key role in the biological energy metabolism. ATP synthesis is found in the bacteria, plants, and animals. Most organisms, the primary function of the enzyme is ATP synthesis from adenosine diphosphate and inorganic phosphates. ATP synthesis consists of the two regions F0 and F1. F0 causes rotation of the F1 and is made of the C ring and subunits A to B and F6. And F1 is made of the alpha, beta, gamma and delta subunit. Alpha, beta, gamma they remain in the headpiece and delta in the stalk. F1 has a water soluble part that can be hydrolyzed to hydrolyze the ATP. F0 on the other hand has mainly hydrophobic region and they are embedded in the inner membrane of the mitochondria. Together this F0 and F1 creates a pathway for proton movement across the membranes. Now ATP synthesis or ATP synthetase. The enzyme consists of an F0 part bound to the membrane and the projecting F1 part. F0 part consists of the three different protein molecules, that is subunit A, B, C. When hydrogen ions flow through this membrane via the disc of the C subunit, the disc is compelled to the rotate. The gamma subunit in the F1 part is fixed to the disc and therefore rotates with it. The alpha and the beta subunit in the F1 part, however, cannot rotate because they are locked in the fixed position by the B subunit, which is anchored to a subunit in the membrane. As the gamma subunit functions in an asymmetrical exile, the beta subunits are compelled to undergo the structural changes described in the figure above. So in my next slide, I am showing the another fine structure of what F1 particle, which has been showing there is alpha, beta, gamma, A, B, C, everything in details. So this is the F1 particles and this is the F0 particles. Together is not the F0 and F1 particles. So how, what is the distributions, okay, of all particles it is shown here. And here you see when this hydrogen proton will be channeled through this F0 and F1 particle, then it will help in the activation of the ATP synthesis enzymes, and ATP synthesis enzyme it will help in the coupling of the ADP and inorganic phosphate and the liberation of the ATP. So this there is F1 and F0, there is F0 and F1 particle is present. It is present in the bacteria, it is present in the mitochondria, it is present in the chloroplast. Okay, the structure almost it is universals. Okay, so structure is this one. This is present in the bacteria, this is present in the mitochondria, and the chloroplast. Since our chapter is a mitochondria, so we have given more focus on the mitochondria. So in my next slides, just I am showing the different mechanisms. Okay, how this ATP what it is accepted by this F1 particle, different unit of the F0 and F1 particle. So here I made it shown. So this is the ATP. Okay, this ATP broken down into ADP plus inorganic phosphates. Okay, again ADP and inorganic phosphate. What happens? First it is in a beta subunit, then it goes to this is the beta. Okay, from this beta again it will be coupled, and ultimately the ATP synthesis will take place. Okay, so these are the different mechanisms. That is not essential to just to understand to get the idea that all the subunits it is not the static, it is dynamic. Okay, always it is moving, and ultimately there is a coupling of the ADP and inorganic phosphate takes place, and this is the energy, this is the ATP coupling. Okay, these are different mechanisms. Just we try to get one idea how this coupling takes place. Okay, so at last I would like to give one note on ATP synthase. This is complex 5. The electrochemical potential energy generated by the proton and pH gradient across the mitochondrial inner membrane is called the proton motive force. Okay, and is used by to drive the ATP synthesis. Proton return to the mitochondrial matrix through an integral membrane proteins of the mitochondrial inner membrane known as the ATP synthase. ATP synthesis is a multiple subunit complex that binds ADP and inorganic phosphate and convert them into the ATP. Proton transport is coupled to the ATP synthesis. This is called the chemiosmotic theory of the oxidative phosphorylation. ATP is not synthesized unless there is simultaneous transfer of the hydrogen proton across the inner mitochondrial membranes. In my next slides, I would like to show the ATP and ADP translocase. ATP and ADP do not diffuse freely across the inner mitochondrial membrane. A specific transport protein, ADP plus ATP translocase, okay, is an antiporter that exchanges each ATP from the matrix for an ADP from the cytosol. Exchange occurs by the mechanism of the translocase eversions. ANT, which is popularly known as adenine nucleotide translocase (ANT), has a single nucleotide binding site, and ADP and ATP have the same binding affinity. When there is a positive membrane potential, that is higher positive charge outside, okay, when ATP is bound to matrix site, the ANT undergoes a rapid eversion, that is, since ATP has an extra negative charge. A fourth energy harvested in the ETC is by ANT. So in my next slide, and the final slide, just I like to show the overall reaction of the glucose oxidation. Now when one glucose molecule C6H12O6, it will be oxidized with only 6 molecular oxygen and 38 ADP and 38 inorganic phosphate. It will liberate 6 molecules of carbon dioxide, 6 molecules of water, and 38 molecules of ADP. In some books, there is a, instead of 6 oxygen, it may be, then that means 12 oxygen. If it is 12 oxygen, then there is liberation of 12 water. That doesn't matter. Our main purpose is the liberation of the, that is ATP. Okay, one glucose molecule, it will give rise to the 38 moles of the ATP. Okay. Now, two hydrogen when transported to the our from this F1, F0 and F1 particle, there is liberation of the 3 ATP. Okay, and 1 ATP it liberates 8000 kilocalories of heat, that is energy, that is a biological energy, and 38 molecules of the ATP, then it will liberate how many? 3,04,000 kilocalories of the energy. This is the overall reaction of the glucose oxidations. And in my last slides, just I am showing inhibitors of the oxidative phosphorylation. Now there is some poisons or inhibitors are there. Okay, sometimes that inhibitors, it will break our complexes, as a result of which it cannot perform these activities, and oxidation will not occur. As a result, our body will deficient of the oxygen energy, and the body cannot perform the activities. Okay, so what are the inhibitors of the oxidative phosphorylation? The complex one is rotenone, complex 2 is carboxynes, complex 3 is intimacin A, complex 4 is cyanide, azide, carbon monoxide, and ATP synthesis is oligomycins. ATP and ADP translocase, that is atracyadyl sites, a plant glycoside. So with that, I would like to conclude regarding your structure, functions of the mitochondria. So already in my earlier classes also I have taken details of this how the different structures of the mitochondria. This is a very important chapter, because the question may come from the structural point of view, or question may come from functional view point of view. If the structure comes, you can give the structures or detailed structure I have given. Now yesterday and today I finished the functional, different functions. So already I have mentioned in my very first slide that function of the mitochondria is very complex and complicated. For the convenience of the study, it can be divided into 4 steps, which is known as glycolysis, and then pyruvic acid oxidations, and then Krebs cycle, and then electron transport system. After that, what will happen? Last stage, which is known as oxidative phosphorylation, which helps in the conservation of the energy. So I think the student, you will follow it. If you face any difficulty, let me know. You are not giving any response, it hurts me. So try to give a response, so that I will be also inspired by you, so that I can prepare my next chapters nicely. Okay, with that I would like to conclude. Best of luck. Thank you. Rashmi? Rashmi? My daughter is helping me.